In this lesson, we're going to continue where we left off. So just to recap, over here I have my impulse, so I have the particles that are going to be emitted. The next step is to create the velocity for them. So let's start by creating a visualizer for it. So new marker is going to be v, v, and v. Set it to be a vector and 0.2. Okay. And again, we're going to do this the same way we did for the previous effect. We're going to deal first with the direction and then with the amplitude. So I'll call this bel-dir for direction. And let's go inside. So one difference from this effect and the previous one is that our pieces are already moving. So they already have some velocity that they're going to have to inherit. So in this case, we can't just make up our own velocity. We're going to have to work with this one. So I'm going to normalize it. And one thing I like to do is I like to mix this velocity with our normal. And right now, I don't think we have any normal. You can actually check. Yeah, there's no normal. So just something very easy. Before we delete all the geometry over here, we can create a normal. And let's set it to points. Okay, let's go back here. And let's connect over here our normal. And let's promote the bias. And I'm going to call it, this will be our V bias. So I'll call it bel bias. And again, let's normalize the result. And this will be now our new velocity. So let's connect it to there. Okay, and we can see if we do this, they will inherit 100% the velocity of the debris. But we don't want them all to travel exactly the same. We want them to shoot outwards a little bit. So using the normal is a nice idea. So maybe something like this. Basically, it's going to open them up. Yeah, I think that will be good. And then the other thing we can do is add some noise. So let's go over here. Create an NTLS flow noise. And I'm going to promote frequency, offset, amplitude, and roughness. And it's going to be a 3D noise. And let's again just normalize this. And we can add another mix in here. And again, let's normalize it one more time. And we're going to call this our noise bias. Notice how I actually connected the noise in the second input. It's just I like to have, well, basically I like the bias if it says noise bias. If I have it set to 0, it means there's not going to be any noise. And if it's set to 1, there will be noise. It's just easier to understand when you look at this. So let's see if we set it to 1, it's going to be 100% noise. So let's start adding our frequency. Now let's see. I'm going to bring down the roughness and I'm trying to find just enough variation within the frequency. I don't want them all shooting off in the same direction. So maybe something like this. And let's add back a bit of our roughness. Maybe something like that. Okay, and now we can bring down the actual bias. So let's see. We don't want that much. Maybe something like that. Okay, and next we can do our another point bump, and this will be our magnitude. So bel mag. Okay, and also the difference between this and the previous setup is that our velocity already has a magnitude. So if we go back to this one, this already has a speed. So we don't want to make up our own because it will look weird. If we emit pieces and they are actually coming off from the debris faster than the debris is going, that's not going to look natural. So what I like to do is actually to store the speed. And an easy way of doing that is if you add a point velocity, and you can add it, let's see, before we delete any geometry. So in here, we can tell it to calculate speed and keep incoming. So what this is going to do, this is just going to create a speed attribute for us. There we go. So it's just going to save the length. For us, it's just, you know, for convenience. We could do it ourselves, but that's just, you know, another way of doing it. What we can do now is we can bring in our speed. And we can just do this very simple. We can just multiply this by the speed. And now that will be our new velocity. So you can see now our vectors are actually, we maintain the length. So it's going to inherit the right velocity. And then the other thing I'd like to do is just add noise again. So NTLS flow noise. This time it's going to be one dimension. So let's promote all of these. And again, we can fit it so we don't get any negative values. And in this case, I don't know, we can go something like that. And let's promote this. So this will be our min noise and max noise. So min noise, and then this is our maximum noise. Okay, and we'll just multiply this as well. There we go. Let's see, for the amplitude, we can try something like 2, for example. Okay, and let's see, so the minimum noise, it's not going to be 0 because we don't want them to not move. We can say something like 0.5. And here for the maximum noise, since we're multiplying with our existing speed over here, I don't want to go above 1 because the maximum these pieces will travel is the inherited speed. So we can just leave at 1. So the one we'll really care about is the minimum noise. So some of them might go slower, but definitely none of them should go faster. Okay, now let's start increasing our frequency. Let's see, probably something like what we had above, like around 15, 18. So that's giving us a nice breakup. Okay, and that looks good. And then the other thing we have to do is we can now go, I'm going to set this to manual mode. And we can go back to our bullet impact because there's no need of redoing this. We can actually copy all of this. So set mass, bounce and friction, create orient, attribute randomize, and this point bob. So let's go here. Let's just paste it. Okay, so for set our mass, bounce and friction, let's make sure that we're not using any custom attributes. So we're just using point number. So that's fine. We're creating an orient. We're creating our angular velocity, and here we're just adding a random amplitude to our angular velocity. Okay, we can go back to auto update. And let's make sure. Yeah, so actually you can see we're inheriting a lot of attributes like orient, W. I'll make sure that we delete those and we have our own. So let's do an attribute delete. So maybe after our point velocity, let's see. We don't want the orient, we don't want the speed, we don't want the color, for example. Okay. So now we have our own orient and we have our own velocity and our own angular velocity. I also saw in there some UV stuff, so we can delete that as well. Okay, and now we're ready to go into pops, and again I can copy that. Let's go back to manual mode. Let's copy this ground setup. Actually, we can copy also the DOP import. Let's go back here and we can paste this. Okay, back to auto update, and okay, and let's update our ground. So let's go here to delete, and we can ghost other objects. And let's see, we probably want to keep this area around here. So let's click select. maybe keep, yeah, I think that area will be enough. So now we can hide the other objects. Okay. And if we go into the popnet, we'll probably have to change the start frame. So let's see, our start frame is going to be, I think, 1048. I believe that's when things start to fall. So let's see, let's go inside. Yeah, there we go. Let's turn off our visualizer. Let's see what this looks like. Cool. So we'll definitely have to adjust some of the values, and I think we might have way too many particles. So actually, let's go back up. Let's go to our scatter here, and we can say times maybe 1.5. Okay. Let's see now what we get. Cool. All right, there's one thing missing, and that is we need to add our colliders. Right now, you can see some parts are falling. That's because we need our wall here, and potentially we can also add the debris as colliders. We covered the very basics of collisions, but we didn't have to create our own yet. We were letting the terrain object handle it. But in this case, our debris are animated, so we're going to need an animated collider. And the best way of dealing with that is to create them yourself in subs, so you have absolute control. Remember that you can still connect our deforming pieces in here, and you can let the pop solver handle that. So let's go into the popnet, and I'm going to create a static object. So instead of using a terrain object, that only really applies for terrains, I want to work with the static object. And this is actually exactly the same as a terrain object. You can give it a subpath, and then it will convert it into an SDF for us. If you go here to collisions, it's the same menu. But in this case, I want to take care of it in subs. So let's go back up, and we're going to create our own collisions. So let's go here to time blend. And the best way to do that is there's a collision source. So this node is going to create, on this side is going to give us a geometry representation, and on this side is going to give us an SDF. So if we visualize this, by default, the first input, nothing is going to happen. So we're going to have our debris geo collision, and actually we can append everything with, let's see, call for collision, and then I'll copy this and paste it, and we'll call this our debris SDF. So if we look at this now, there's probably nothing, and that's because if we go here to volume, probably have to change the voxel size to, let's say, 0.1. Okay, and now we're getting something. And you can see that this is, if we let the solver do this, it has to do it every single frame because this is moving, right? And the nice thing about doing it here is that we can cache it. So that's going to make our sim a lot faster. So we can go to file cache, and let's see. So cache, collisions. We can create another folder, and we can call it debris, and it's going to have just the operator name, just like that, and we can call this our debris. Okay, and now we can tell it to save to disk. I'm getting an error. I think that's because our geometry doesn't exist. So we can add here a time shift, and let's clamp it to first. So 1001. And whenever you add a time shift after a time blend, you want to make sure that you uncheck integer frames, and you change this to $FF. That means, so $F means it's a global variable to refer to the current frame number, but as an integer, $FF will refer to it as a float. Okay, and now we can save to disk. And you'll see this is going to save us a lot of time, because if not, this is all time we would be spending every single time we would make a new sim. We would have to calculate, and we'd have to wait for all of this. I'm going to change the file mode to automatic. Okay, and we should see now reading this cache is now a lot faster. So we have our own collisions. And I'm going to do the same for the wall. So I'm going to object merge the wall over here. So it's the environment. So this is the wall dented out, and by default this is packed. So I'm going to convert it. And I'm also going to create this collision source. And let's copy one of these null nodes. So this will be collision, the wall geo, and this is going to be on the other side, the SDF. So it'll take a while to compute it. Again, you could cache it, but this one isn't time dependent. So SDF. Okay, and I think actually it's extremely high res. We can probably increase this a bit more. We don't need that much resolution. Something like that will work. Okay, so let's see how we can add this in DOPS ourselves. So if we go back here, we go to the static object. You can specify the minimum thing you need for this to work is to specify a subpath. So in our case, that's going to be // collision, and you want to connect the geometry in here. So in this case, I'll call this our debris collision. And if you connected this into here, let's say I'm going to add a merge, just so we merge all of our colliders together. So if we did this, the solver would be creating the SDF representation itself. As we can see, if we go here to the output, and let's actually turn off display geometry, and let's display over here the collision guide. We can see actually there's nothing, and that's probably because it's, again, really, really small. So let's see, maybe 100, maybe 250. There we go. So now it's starting to show up, and even some of them. So we don't want to do this. We want to use our own SDF. And the way to do that is you can change here the mode from ray intersect to volume sample. That means that it's going to be sampling a volume from subs, and the path where you specify where that volume is here. So in here in proxy volume, I'm going to tell it // collision debris SDF. Okay, and now as you can see, it's loading that volume. So we don't have to worry. All this now becomes irrelevant. It's just loading our collisions from here. So we can turn this off. And we can turn this on. So the nice thing is now we're going to have pretty accurate collisions. And now let's copy this and do the same for the wall. So in this case, if you're wondering why we have both sub and the proxy volume here, it's just the sub is just a nice representation for it, right? Like we just want to see the way it would look like. So we don't have to worry about the collision. That's for the solver to handle. But the subpath is just doing that in this case. If we're not giving it a collision geometry, then it will create the collision geometry based on that. But in this case, this is just for display. So we can say this to wall and set this one to also be the wall. Okay. And let's see. So by having the debris in here, we might end up having crazy collisions. So actually, let's have a look. And I think it's fine. Okay, and these pieces are obviously sliding way too much now. And the bounce doesn't look like that good. So let's start fixing that. Let's see, we can't even see the big chunks anymore. I'm not sure they're even there at all. Oh yeah, I forgot. So one big detail, we're not using the forming geometry. Ah, there we go. So it's very important whenever you're using geometry that is changing every frame, you need to enable this, use the forming geometry. Actually, if not, it's going to just default to what the pieces are in the first frame. Okay, now we can actually see them. Cool, and now we can just go back and let's see, let's start tweaking our parameters, especially these ones. Let's see, we can show all the objects. And the thing is, we won't really see much, yeah, from this side. So we don't get to see how it settles and all those things. So we don't really have to spend much time on it. Let's see. So I'm just going to increase the friction a little bit more. So maybe something like that. Actually, we can hide the other things for now, just so this gets real time again. There we go. Yeah, maybe even more. So let's say 0.2. And let's take this one to 75. Okay, that's slowing them down a lot more. And then here for the bounce, again, it might be too much, so let's change it to 0.4 and maybe 1.5. Okay. So let's have a look at how it all looks together. We need to turn off the grid, switch to the camera, show all the other objects, and let's create a flipbook. Okay, it's done, so let's hit play. Cool, this is complementing our effect a lot more. One thing I don't like is I think they're too slow, and that might be because I turned it off. Since we're copying everything from this popnet, over here our inherit velocity is set to 0.82, so let's change that back to 1. Let's make sure we don't have anything else in here. I think the rest is pretty standard, so let's try one more time. Okay, it's done. Cool, I think that's definitely adding a bit more velocity. That looks nice. Okay, now it's time for the last part, which is just to instance geometry onto those points. So let's see, let's go back here, and I'm going to create a clean node in here. So let's see, let's not kill those, but we maybe want to remove, let's have a look. So we definitely want to kill all these attributes, but we want to keep maybe the debris. So let's see, all except the debris. Then the ID for sure. Then we have the impact ID as well. So those are all useful things that we might end up using. We have the mass, the orient, so mass, orient, probably velocity and angular velocity. And let's see if I missed anything else. So no, I think that's all. Okay. So now we're ready to create a new p-scale. So let's just go into a new point bob. And we're going to bind the mass. And we're going to fit it from 0.75 and 1.25 into our minimum and maximum. So let's see, min p-scale, and this will be our max p-scale. Okay, and now this is going to become our new p-scale. Okay, let's go back up, and let's see, we can now create a sphere. And I copy 2 points, and let's try to get roughly the size. So let's change this back to polygon. So I like to set this one to the distribution, so maybe like 0.1, 0.6. And for the actual size of this, we can change it here in the uniform scale. So it's going to be pretty small, like 0.1. Still too big, so 0.15. And let's turn off over here the guide geometry. So this might work. It'll be a good idea to look at it from the camera point of view. Let's see how close we get to them. And also to make them more visible, I'm going to color them gray. Same as the color from the, basically from the concrete. Let's see. Yeah, something like that, maybe a bit lighter. Okay, let's see how small they are. Actually, they're not that small. They're pretty fine. They're supposed to be pretty fine particles. There might be too many of them, but that's something we can easily fix. Let's see. So let's go to the scatter over here. We can change this to 1.25, for example. Let's go to that frame and let it cook. Let's keep moving. Okay. And now I mentioned that we were going to look at a different way of instancing geometry. So instead of simply copying the same geometry onto every point like we did before and like we're doing now, let's have a look at how we can add some variation to make each copy unique. For that, we're going to be using a for loop. So let's go here. We're going to create a for each point. And what this will do is just loop over every single particle. Let's hide everything else for now. And let's have it cook, okay? So let's just have a look at one point. And I'm going to connect all these things inside here. So now the input of the copy to points, the second input will be there. And then the output is going to be there. We can have the color at the end. So basically I want the copy to points to happen inside of the for loop. And I'm going to create a point jitter. So we can go here. And let's have a look. Let's zoom in. So that's definitely too much. So let's say 0.1. See how big it actually is. Okay, still too much. So let's say 0.1. Okay, something like that. Okay, and to make each copy different, we have a seed over here. So what I like to do is every time this for each runs, I like the seed to have a different value. What we can do now is have the point jitter selected, and we can go here and we can tell it to add a spare input. And over here, I'm just going to drag and drop the for each begin. And you'll see this is going to create this purple arrow, and it's going to include the point jitter inside our for loop. And now what this allows us to do is we can use an expression to refer to whatever is this point. And one thing that changes with every point, as you can see here, is that they all have a unique ID. So in theory, we can grab the ID and we can say that the seed will be equal to the ID, for example. So all we have to do is say here is say point, and here, instead of giving it a string to that path, I'm going to type -1. So -1 refers to spare input 0. Then for float, it's going to be 0 because that's the point number. It's always going to be 0.0. Then the attribute we want, which is the ID. And finally, the index. So it's a float, so just 0. So as you can see, this is going to return that number, which is our current ID. And that number is going to change for all the other copies. So let's see. Let's have a look at what they look like. It's going to take a while for it to run. Okay, let's look at the whole result. And we should see now that each one of them is going to be different, right? Because we're using a different seed. And now a way to make this faster is to use the compile block. So let's type compile block. And the way to use this, one of the requirements is that everything that comes into the for each loop needs to have a spare input. So we need to go into here and create a meta import node. And here we have to tell it to fetch the input. And I'm just going to connect it here. So this is just a requirement that the compile sub needs. I'm going to cancel this. So let's set it to manual. So everything that's connected, it all has to be brought in by this for each with a fetch input. Okay, and then let's add some space. And I'm going to add the compile begin in here and the compile end in here. Okay, let's move it over here. And The same applies for the compile begin. We actually have to have everything wrapped in these nodes, just like that. So that's all you need. The last thing we have to do is select our for each, and we can tell it that this is multi-thread when compiled. And let's see, let's go to auto update, and we should see now this is going to be a lot faster. And let's see if you get an error. Okay, just recompile, and there we go. Now we have all just unique copies in here. The disadvantage of this is that, of course, it takes a lot longer since it has to do this every frame, but it's not that slow. You can see, especially now with the compile end. So let's have a look at what this looks like. I'm going to go into show all contents, go into the shot camera, and let's make a flipbook. All right, and this is done. So let's have a look. I think we ended up with way too many pieces, and they're actually a bit too big when you compare with the actual size of the debris. I mean, they're a bit too overpowering. Like, the debris are way too small compared to that. So I think, yeah, especially here, they're a bit too big. So let's see, let's actually go back. So let's see how many we actually have. So we have, if you go to the last frame, we have almost 1.7 million. So yeah, we definitely want, let's see, even, I'm going to remove this. So let's say maybe a third of that, or a fourth. So let's divide by 4. And same with the p-scale, although we'll see the p-scale at the end. Let's see. And actually we have to get our simulation to run again. So let's reset it. Okay, and now let's go back a few frames. Let's see how many pieces we have. All right, so now we have 500,000, and I think they're still big. So let's see, let's go with 1, 2. And we'll probably have to change also our point jitter to, let's say, 1, 2. Okay, and let's do a new flipbook. Okay, and it is done. So I think now we may have way too little, and actually it doesn't look like some of these particles are spinning much, so we have a few things to fix. Let's see, let's go back up. The one thing I'm happy with is the size. But let's see, the scatter, we can say divide it maybe 2. And let's try here with our angular velocity. I'm going to do this times 4, and this one times 5. Let's see, that gives us at almost 3000 for our max angular velocity. And let's do a new flipbook. All right, and this is done. So let's have a look. Yeah, and I think this is much better. I think the size now works. Also the amount works a lot better. We can see that based on the holes and the amount of material that's coming off of the wall, the amount of debris that we see is a realistic amount. Let's see if we can see a bit more of the spinning. Yeah, I think, well, this is it. So in the next lesson, we're going to have a look at the car crash that happens right after this.